Well, hello everyone again. We are here for our second session of the last day of AstrotwinColo with Cristina Garcia, and I will be here behind the scenes, just checking for your questions on the YouTube chat, so I can pass them along to Cristina. So, is there anything else for now? I don't think there's anything else. So, I will leave you with Cristina now.
Thank you. Okay, then we will continue. I'm gonna share screen. Okay. Okay, so in this last part of the last lecture of this week, I'm gonna actually wrap up a little bit all the information that we have been learning this week. I will highlight the most important points, and then we will have our final quiz for today. Then maybe this will be a little bit. We'll finish a little bit earlier than the schedule. But I just want to take the time to summarize somehow what we have learned this week. Then for this, I'm gonna show you here this slide that I took from lecture number 1, in which I mentioned several interesting questions related with the large-scale structure of the universe that I was expecting to teach you, and I was expecting you to be able to answer at the end of this week. Then I'm just putting this again here, then you can really check if you now understand and can now say something about those different points. In general, I think that we have covered all of them, and probably you can you now know much more than the point that I'm showing here. Then this is just for you to make a check. I will just summarize in general terms with those schematic view that I have trying to show you during the week. I have showed this one in particular several times, but it's never enough because this show very nicely the evolution of large-scale structure of the universe. Large-scale structure of the universe is defined as everything larger than a galaxy. Then here you can show that everything started at the Big Bang. We had an inflation process at the beginning of the universe that we described in lecture 1. And we have an observational proof of what was the matter distribution just after the inflation at that early cosmic time. I show you that dark matter distribution grow over time, in which matter overdensities become more overdense with time, and matter underdensities become less massive with time. This is just a result of instability, gravitational instability that I explained you using some equations. I kept this very qualitative because to really understand this mathematically, we need to understand much better cosmology, and I didn't want to go at that level of details. I also showed you that at some regions, in some regions of the matter distribution, the matter can start collapsing under certain criteria of mass over densities. And I also show you that those collapsed structures are called dark matter halos, and are the locations in which galaxies can start forming. If you really want to understand how a galaxy can form within halos, I really suggest you to learn about galaxy formation and evolution. And you can find actually a summer school some years ago from the AstrotwinColo also that was related with this topic. But in general, you know now that a halo can contain several galaxies too. I also show you the distribution of galaxies in our local universe, which I'm showing here based on the Sloan Digital Sky Server data. And you can now understand that it is a very complex process to really interpret what we are seeing here, because we need to understand the growth of structure over time. We need to understand cosmology. We need to understand how halos form in the universe, and we need to understand galaxy formation and the distribution of galaxies within halos. Then that is a very complex process. I try to make an overview, a general overview about all of this. We also in lecture 2 talked about how we can measure the correlation function. I defined this quantity based on the probability of finding galaxies above a random probability. We define the correlation function. I show you that this is the typical shape that we find with two important parameters, R naught and gamma, which are the parameters that we actually need to constrain. Those are the observable quantities that we have to constrain large-scale structure of the universe. All the other parameters are just we require models and simulations to translate those observable quantities into halo mass, bias, or others. I also explain you how can you measure the 2-point correlation function in the practice, depending on what was the data available. Then I told you that with 2D positions, with 2D data, you are only able to measure an angular correlation function, which is more affected by projection effects and also is more noisy, but we can anyway measure and constrain the R naught and gamma parameters using only 2D position of the sources. In the ideal case in which you have 3D positions, I explained you that you can measure the projected correlation function, which is less affected by uncertainties, and this provide a direct measurement of R naught and gamma without any assumption about redshift distribution or about cosmology. We also saw a review or an overview of the clustering dependence of on galaxy properties, and I show you the different measurements of the correlation function for different type of populations. This is very nicely summarized in this figure, in which we have different type of populations having more strongly or less strongly clustering. We also can measure the clustering of objects at much higher redshifts, but still we still lack a lot of information to really perform more precise measurements, especially at the highest redshift, and especially at other wavelengths different than the optical wavelengths. I already showed you this at the beginning of this class, and I'm not gonna repeat again the history, but basically we learned that dark matter halos and galaxies are biased tracer of dark matter, and we learned about how can we understand this statement and how can we then interpret our clustering measurements in terms of the mass in which different population inhabit. We also learn about these useful relations, about the correlation length, the bias, and dark matter halo mass, and more based. Well, I already mentioned this at the beginning of the of the lecture, that we really can learn about galaxy evolution using clustering measurement. That was one of the questions that I included in lecture 1. Then I think that I have provided already a very convincing argument that we really can't constrain evolutionary links between different populations at different cosmic time just using just using correlation function measurements and models of growth rate of halos. More focused on what we learned today, we understood why we measure a power law shape for the correlation function. I explained you that this is the result of the contribution of two terms, the one halo and the two halo term. That comes from the fact that we are counting pairs at a small scale in which galaxies are within the same halo. And the two halo term comes more from galaxy pairs coming or inhabit different dark matter halos. Then this result in two different components for the correlation function that all together makes us to measure power law shapes for basically all the type of populations in the universe. I also talk a little bit about the halo occupation distribution models, which are very important to interpret our observations of correlation function, and provides very useful insights about physical processes dominating or impacting the evolution and formation of galaxies for the different populations of galaxies. Then maybe the main message here is that I already said that in lecture 1, I think. We really need both observations and simulations and models to really understand all those processes. Clustering measurements by themselves don't provide so much strong information if we don't combine this with simulations and modeling. We really need those to interpret our observations. Finally, I also show you that using just clustering measurement, autocorrelation function, and cross-correlation function, we can also make some statements about physical processes in the environment of some galaxies. In particular, I talk about the quasars environments, and just based on clustering measurements, we can more or less understand or demonstrate that probably galaxies around quasar are more dusty compared with galaxies in random locations. Then yeah, that is all for today, actually. I have now a Kahoot that I have prepared for you. Then we can check how are you following this lecture.
Hi, Cristina. Sorry, yeah. There's one question that I think sure. You might want to answer before the quiz.
Yes. Based on the current data and models, what is the most likely long-term fate of the universe? Wow, that is a big question, actually.
Was that included in your quiz?
It's not included in my quiz. That is actually very hard to answer. What I can say about long term, one thing that I can say is that at long term, dark matter halos and galaxies will trace much better the dark matter distribution. That is something that we can already say about the future. As I show you in this model before, we know that currently dark matter halos and galaxies are biased tracers of dark matter, but we expect that at longer times in the very future, for example, galaxies and dark matter halo distribution be unbiased tracers of dark matter. at long terms, that will be something, for example, that we expect. What else can I say? I don't know. In terms of cosmology already predict more or less what is the fate of our universe in terms of expansion. Then, but in terms of large-scale structure, yeah, that it is. And maybe also mention that currently we also have, we have cluster of galaxies in our local universe, but you also may know that we also have supercluster of galaxies, in which clusters are coming together to form these superstructures. Then I guess that in the future, this also will be reflected as unbiased tracers of dark matter, I guess. But yeah, I don't know what else to include in this answer. It's really a hard question. I guess that more data is always useful to put more constraints on the fate of the universe. But most of the correlation function measurements and large-scale structure so far is more to understand our current observation and our current universe. Yeah, sorry if I cannot provide a more deep explanation about that. Okay, then let's play now with this Kahoot. Okay, then you should be able to see the game theme now. Okay, then I'm gonna wait a little bit for you to join us and play for the last Kahoot of this week. I'm gonna wait a little bit more in case more people is joining. Thanks all the people that has been playing the Kahoot every day. The nice that you are here in real time. Okay, I think there is not more people joining. Then I will start now. Full screen. Okay. So the first question is, the exact shape of the galaxy correlation function depends on cosmological parameters, how satellite galaxies are distributed within halos, or both of them? Okay, everyone already replied this. Okay, several people respond this one, how satellite galaxies are distributed within halos. Well, the right answer is both of them, because I explained you that the shape of the galaxy correlation function depends on two terms, the one halo term and the two halo terms. The one halo terms is dominated by how satellite galaxies are distributed within halos, but we also need the information of the 2-halo term, which is more related with how halos, dark matter halos, are distributed in the space, and that is this can be described using cosmological parameters. Then that is why the red option here was also correct. Okay. Question number 2. The shape of the 2-halo term in the correlation function is dominated by the radial profile of galaxies within an halo. True or false? Okay, well, the answer is false. The 2-halo term is dominated by the distribution of dark matter halos in the universe. The one that which is dominated by the radial profile of galaxy within one halo is the 1-halo term, because this is basically based on the number pairs of galaxies at small distances. Then that was false. Okay. This is a true or false question. The shape of the 1-halo term in the correlation function is dominated by the Navarro, Frank, and White profile. True or false? Great. All of you answered this correctly. Yes, the 1-halo term is dominated by whole galaxies are populated within 1 halo, and that is well described by the Navarro, Frank, and White profile, which also describe how dark matter is distributed within 1 halo. Then that is correct. Okay, question number 4. How can we know what are the parameters of halo equation distribution models that better describe our observations? By fitting the galaxy correlation function over small and large scales, by fitting the galaxy correlation function over the 1-halo term regime, by fitting the galaxy correlation function over the 2-halo term regime, or by fitting the correlation function of dark matter halos. Okay. Well, only one person put the right answer. HOD models actually include everything, include the cosmological models, and include all the distribution of galaxies within a halo, include some physics related with that. Then that should be reflected over all the scales. in our correlation function measurements, then and some people answer fitting the correlation function of dark matter halos. No, actually, because the correlation function of dark matter halos is actually not possible to observe. That is only known from simulations. Then we normally fit our observed clustering with HOD model, and we can then make some conclusion based on that. Okay. Next question. If we want to know what fraction of the most luminous galaxies are located at the center of the halos, we have to use simulations to measure the halo mass in which luminous galaxies lives, fit a Navarro-Frank-White profile to the observed correlation function of luminous galaxies, fit HOD models to the observed correlation function of luminous galaxies, or there is no way to know that fraction. Okay, well, you replied this quickly. The right answer was fit HOD model to the observed correlation function of luminous galaxies, because I already show you with one example that, for example, using HOD models, we could learn what was the fraction of satellite galaxies for the case of red and blue galaxies, for example, that we use to interpret our observations. Then in the case in which we want to know that fraction for the most luminous galaxies, we need to measure first the correlation function of that population, and then compare with HOD models. Okay, great. And several people reply, fit a Navarro-Frank-White profile to the observed correlation function of luminous galaxies. That is not true, because that don't tell us about what fraction of the sources are in the center of halo. That is true that could be a little bit a bit informative, but it's not providing the complete answer for this question. Okay, question number 6. What is the main reason of why we use quasars as tracers of overdensities in the early universe? Because they are extremely luminous, because they are strong, they have a strong clustering at high redshift, because they are detectable at several wavelengths, or because we can easily obtain their redshifts? Okay, most of you got this very well. Then it is also true that quasars are very luminous, and that is a little bit more easy to obtain their redshift, and it's also true that are detectable at several wavelengths, but those are not the main reason why we choose those as tracer of overdensity, but it's more, the argument is more based on their clustering. Okay. Question number 7. High redshift quasars are located in the most massive halos in the early universe and are surrounded by galaxy overdensities. Is this true or false? Okay, that is actually true, and I spent several slides showing this result. This is true based on what we have learned so far. It's true based on measurements of autocorrelation function of quasars, and it's also true based on galaxy quasar cross correlation measurements, and those two measurements are more or less independent. Then so far we really believe that high redshift quasars are located in massive structures. Okay. And this is the last question. What is still missed to better explore evolutionary links between different populations across cosmic time? More computational power to process large amount of data, larger and deeper surveys at different wavelengths, a better understanding of cosmological parameters and halo formation, and more detailed numerical simulations. Okay, great. Most of you got the right answer. This was actually a tricky question because, to be fair, I think that all of the options are still needed to improve, but we more or less understand pretty well the cosmological parameters has been well measured so far. And we also understand pretty well halo formation. And that is just because we have detailed numerical simulation. But that is true that we still can make more progress in terms of numerical simulation to include more physical processes and other things like that. Then that is also something that have to make some progress in the future. And also computational power will be also required, especially for clustering measurements in which you have to compute a large number of distances between sources. Then as long as we will be obtaining more and more data, we will need more computational power too. But currently, the more missed things I would say is to get larger and deeper surveys, and specifically at different wavelengths, because currently we have been exploring mostly optical wavelengths, and we really are behind in radio wavelengths or submillimeter wavelengths. Then that is, in my opinion, the part more needed right now. Okay, and that was all for today. Let's see who win. Great, Ale, you were the third one. Jamie, the second one, and the winner was Juan. Great. I think that Juan has been winning the last Kahoot, actually. Then great. Congratulations, and thank you for being here. Yeah, and let me stop sharing now, because that is all what I had to show you today. We are 10 minutes ahead in the schedule, but for the afternoon, I prepared a last workshop in which we will use a real image and we will learn how we can generate random catalogs to measure the correlation function using real observations, which is a little bit more different to what we have been doing in the past workshops in which we work with simulated catalogs. Then I would like to show you a little bit more the real world in terms of clustering measurements. Then please join us in the afternoon. Yeah, that is all for now. Thank you for participating this week in the summer school.
All right. Thank you very much, Cristina. So there is a few minutes if you have questions. If maybe someone in the chat wants to ask something.
I can see one question actually. Luisa, do you think 50 meters, millimeter telescopes could provide these deeper, larger surveys, or do you think interferometers are better for understanding clustering? That is an interesting question. I think that at least with the current interferometers that we have at 2 millimeter wavelengths, which is basically VLA and ALMA. With ALMA, it's actually very hard to constrain clustering because ALMA has a small field of view, and we will need to cover very large areas and target a lot of pointings. That will be very expensive to make with ALMA. Then ALMA maybe is not the best instrument to measure clustering. I think that currently the single dish telescopes can make this possible as long as the angular resolution is improved, because angular resolution also impacts the measurements of clustering. But as long as the angular resolution is smaller, the impact is also smaller. Then I guess at 2 millimeter wavelengths, single dish should provide a better survey for clustering measurements at this moment.
All right. Thank you again, Cristina. I think we'll reconvene at 10:25 then.
Perfect. Yes.
All right. So
I guess Esteban sent the PDF with the workshop today. I'm not pretty sure if he already sent it or not.
Well, I don't know.
Okay.
I see Esteban on
yes,
the stream, but I don't know if he has an answer for us.
Yeah, he did answer. He already sent the workshop. Then great. Yeah. Anyway, you can also find the workshop instruction in my webpage. Great.
Okay.
See you in a while.
See you. Bye. Thank you.
Bye.